Continuing on, look at the series chapter, we're going to look at something called sigma notation, which I think you've seen before, but we'll go through it again just in case. Sigma is a Greek letter, looks a bit like this. It's a Greek for S, and it stands for sum of, in this case here. We write it with whatever our variable is, R in this case, with a lower value and upper value. It's often from 1 to something. It isn't in this case here. It's often from 1 to something or other. And it's similar to our integration, which is a stretch out S, and that's a sum of various things as well. So the question he wants us to work out the values of them, evaluate this sum here. So we're going to stick 5 in, 15, stick 6 in, well, I'll put the comma for because it's a sum of, so I should be adding 18 and add 21 and add 24. 5 to 8, I've got 4 terms all in all. I'm going to add those together. I've got 39 doubled up, 78. Quick way, if you have to do these, pair them up. 15 out of 24 is 39, 18 out of 21 is 39, double it, 78. Similarly, evaluate this one now. So, this is your typical GCSE look. We're going to sum up 2 and minus 7. So, stick 1 in to get minus 5, then minus 3, minus 1, plus 1, plus 3, plus 5. How many is that now? 1, 2, 3, 4, 5, 6, and then plus 7 and plus 9. And the good news is, first 6 all cancel out, so I've got 7 of 9, 16. Nice and straightforward. Notice that was R equals for the first one, this is N equals here, this one's K equals, doesn't matter what the letter is, the letter doesn't even have to appear in the thing itself. K equals 1 to 2,000 of 3, well we're just adding up 3 2,000 times. So we might as well write 3 times 2,000, which is 6,000. Straightforward. Example 4 wants to work out the answer to this one. K equals 1 to 453, a bit strange, minus 1 to the power K. Well, so let's see what happens when we stick values of K in. Stick 1 in, I get minus 1 to the 1. Stick 2 in, I get minus 1 squared. Stick 3 in, minus 1 cubed, and so on. It's going to alternate minus 1 plus 1, and so on, all the way up to the last value I'm going to stick in, 453, is going to be minus 1 to the 453 is the last minus 1. Well, everything's going to cancel out apart from that minus 1, which is that. Why do we end up with this? Because the K value at the top is odd. If it was even, have an even number of terms, they would all cancel out, the answer would be 0. So in this case, because an odd value at the top, odd number of terms, everything cancels out apart from the last one. I was distracted by the birds tweeting outside then. Example 5. Write 1 plus 8 plus 27 plus 64 plus dot 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 all the way up to 1,000,000 in sigma notation. Well, this is adding up cube numbers. So let's choose a letter. R equals 1 to something or other, and it's going to be summing up R cubed. My last term, 1,000,000, is, well, what's that cubed? 1, 2, 3, 4, 5, 6. It's going to be 100. I'm not asking us to work it out, just write it in sigma notation. Example 6, do the same thing for this series here, not an obvious one. 97 plus 94 plus 91 all the way down to 40. Well, this is going down in threes, so part of our solution must involve, if I'm using R, and it's up to you how you then do this part here. If you want to do it in terms of how many terms there are, start with 1. I need to have the term before being 100, so 100 minus 3R, so the first term is 97, and then so on, and then go down in threes. To work out the top part, I need to think how many terms there are. From 97 to 40 is 57, so that's, if it's going down in threes, that's 19 gaps. That doesn't mean there's 19 terms, it just means there's 19 gaps, because it's inclusive. There's the first one, 1 gap gives me the second term, 2 gaps gives me the third term, and so on. That actually means there's 20 terms there. Okay, so that's one way of writing it. I could use different values there, but they have to go so that it goes from something to something where that's 90 more than that. Example 7. Simplify 2 different sigma expressions in one sigma notation. Well, the good news is it's the same n equals 1 to 50, so I can write it, sigma n equals 1 to 50, And all I do is simply add that function to n and that function to n minus 1 to get 4n minus 1. Nice and straightforward. Last example, they give us a particular summation. Sum of the first 30 square numbers is apparently 9,455, and from that it wants to work out 3 other expressions here. But it doesn't want us to actually expand it and work them all out and put it into formulas, just based on this, using this value here. So this is non-calculator, not doing too much in terms of calculations, with a little bit of knowledge maybe. So n equals 1 to 31 of n squared, well that is the same as adding up the first 30 square numbers and then adding on 31 squared. So all I have to do is add 9455 and now that 31 squared is 961. And then add them together, there's a 6, there's a 1, there's a 4, and there's a 10. 10,416. Nice and straightforward. B is n equals 5 to 30, so I can think of that as being the sigma n equals 1 to 30 of n squared minus bracket 1 squared plus 2 squared, 3 squared plus 4 squared. So it's 9455 minus, what have I got here, 1, 5, 14, 16, 30, which is 9425. And the last one, sigma 1 to 30, n minus 1 squared. There's a couple of ways of doing this. You can think what it actually is. If I stick 1 in, I've got 0 plus 1 squared plus 2 squared and plus all the way up to plus 29 squared when I stick 30 in. Well, all that is sum of n equals 1 to 30, what we had before, n squared, minus 30 squared. So it's just 9455 minus 900, which is 8555. So that's the only bit of knowledge there really, was knowing that 31 squared was 961. I wasn't really doing expansion, not using a formula. At each stage I'm using that 9455 given in the question to work those out there. So the sigma notation then, as I say, a bit like integrals, it's got an upper limit, a lower limit, it's a sum of, stick your values in, work it through, and it's all a bit of common sense really.